Thank you. Big crowd for Friday. Thank you for coming here. My name is Ynal Özkan. I'm one of the solutions architect from New York office. I work with our financial services clients on the enterprise level. And I would like to introduce Amir. Amir?
Thank you. So we're one of the AWS customers. We use AWS to provide software as a service solutions for our customers, who are insurance companies.
Yeah, today we would like to do two things. The first thing is like how Aon Benfield is leveraging GPUs. It's a very creative way of looking at the fleet and how you can manage your calculations using AWS. That's the main part. This is maybe the fifth day of the conference for you. So we will not do too much AWS, but at the end, I will also cover how we are making this work on the back end in terms of AWS architecture, and we will also cover how it works on AWS. But the main focus is like GPUs and how GPUs are leveraged, how Aon is looking at the GPU fleet and the processing power. We will basically focus on that one, and Amir will take it from here.
Okay, thank you. Okay, so brief introduction. My employer, Aon, it's a large corporation. Many of our customers are or insurance companies that have big simulation problems. They want to simulate various types of risks, financial market risks, as well as catastrophe risks and other things. We focus on the financial market risks, but technology is applicable either way. Our software is called Pathwise, so this is something that we run on top of AWS to provide end users at life insurance companies with risk modeling and hedging system. So our Pathwise platform, it has a lot of different components. What I'm going to focus on here is the GPU computing and cloud computing aspects for doing Monte Carlo simulations. This just shows one view of our software stack and how it runs on Amazon. So essentially, there's all this is happening in Amazon or AWS cloud, but our end users are customers, and they VPN into the environment to use our products. So you can read more about our product in NVIDIA's brochures. We work closely with NVIDIA. We're using GPUs. So I don't know, it may be some review for some people, but GPU means graphics processing unit. It's a type of processor. The fact that it's called a graphics processor is basically a historical artifact. So in 3D graphics, as you may know, basically you have some geometry you want to render, and it's represented by millions of points in 3D space that are called vertices. And so you have several million of these points. Then you want to run them through various linear algebraic transformations. So you do a rotation, projection, scaling, translations, and then the GPU, and you have to do this very quickly because it's a massive amount of calculation, numerical calculation, that has to be done in near real time to create like a video effect for a game or something. But it's highly parallel, so each vertex can basically be processed by itself. But what we're really talking about is, okay, millions of numbers, and I want to do parallel floating point operations on them. So that's far more general than just graphics. In particular, In financial services, we have very huge workloads for Monte Carlo simulation that are brute force parallel floating point operations, floating point calculations. The graphics processing industry, they first started by just making hardware. They took this graphics rendering pipeline and put it into like an ASIC hardware, and it was sort of programmable, but it did one task and it did it faster than the CPU could do. So software rendering is just way too slow at the time, but that was kind of a card you put in your server, and over the couple decades, almost 2 decades, that device has morphed into this huge general programmable processor. In the meantime, the Intel or traditional CPUs, we've been riding the computing industry for like 30 years, rode this exponential called Moore's Law for a long time, and that kind of transformed the world. But as you may know, around 10 years ago, they could no longer keep exponentially increasing clock speeds on CPUs. And that has something to do with a physical engineering problem called Dennard scaling, and just can't do it. It's not practical. So we kind of topped her out around 3 gigahertz, although I heard that AWS is overclocking their chips in their data center, but it's about 3 gigahertz. But Moore's Law continues to hold after that, in the sense that we can continue to, for now, double transistor density every 18 months. So you have all these transistors. What do you do with them? So Intel's, I'm sure you know, they said, okay, let's make like a dual core chip. Just take 2 CPUs, shrink them, put them on the same die, and then do it again and put 4, and then again put 8. And then inside each core is actually something called a vector processor, AVX vector processor. So there's parallelism inside one core where you can do like 4 or 8 floating point calculations. If you used to be called MMX, like multimedia extensions. Anyway, there's some parallelism there, but the Intel CPU is really designed for very low latency, complex logic execution. So if you have a whole bunch of if statements and you need to like go through one thread really fast, that's what it's great for. But if you need 50,000 threads to just get done all in total in a short amount of time, that's throughput instead of latency. And that device is not really keeping up with the GPU. So basically a GPU has like 2,000 cores and 8 cores. Those 2,000 cores are not like CPU cores. they're small, they're low, they run at lower clock rates, like 700 megahertz or something, and they lack features. Like you can't run an operating system on a GPU core. It doesn't have like interrupts and things like that. So in the end, what we see is that there's an increasing gap in the floating point throughput of a GPU processor versus a CPU. The graph on the left shows the gigaflops, floating point operations per second, peak theoretical capacity of like a Haswell and a GK210 processor. So it's a pretty big gap. Memory bandwidth is also higher on a GPU. That has to do with, so we call it like RAM, random access memory, but it's not really random access. If you did random access, you'd be going very slow. What you need to do is the machine works in chunks. So if you grab a bunch of contiguous memory all at once, you'll get a better bandwidth. We have 2,000 cores running in parallel. If they all access memory, each core accesses adjacent memory address, then the memory controller will be able to like grab that data from memory at a higher bandwidth than you could achieve otherwise, and they use some more expensive memory, GDDR5 instead of DDR3. But so there's a gap in memory bandwidth. So if you were just, if you had one processor, you were limited to just one processor, and you had to do a lot of like Monte Carlo simulations, obviously you're going to get better performance. Your job will be done in less time if you use the GPU. This is a diagram of the latest processor from NVIDIA. This is 5.2 billion transistors. It's probably the most complex processor that exists today in terms of transistors. You can sort of see how it's organized with all these physical cores, hundreds, or I should say 2,048 of them. But in reality, if you're interested, like, you don't actually give the GPU 2,048 threads. You give it like 20,000 threads. And then internally, it takes care of scheduling those in a way that it can hide the memory latency. So while one operation is occurring, the memory for the next operation is being transferred to cache and registers. And it's all pretty much automated, so you don't have to worry about like other architectures existed in the past, like the cell processor architecture from IBM and Sony and PlayStation 3, and you'd have to kind of manually manage this buffering of data and overlapping calculation and computation, whereas the NVIDIA device takes care of that automatically. So a large part of the silicon is cores and that scheduling, gigathread scheduler, whereas an Intel CPU, a huge amount of the silicon is dedicated to cache and cache coherency. So these GPUs are available in Amazon, which is in AWS, which is a very interesting opportunity. There are two instance types currently, CG1 4x large, it's an older model, and a G2 4x large. These are available on a 10 gig interconnect. If you start them all in the same cluster group, you'll get so 10 gig is pretty good. Between and the G2 or CG1 server is also pretty powerful, so you're cooking with gas if you have like 100 G2s on a 10 gig network. And you can get them with either spot, on demand, or reserved. So just to give some examples, so the G2, each instance gives you about 1,500 cores. So if we were to launch 200 of these, we'd have 307,200 cores. In our software, that allows us to do about 20 million simulations per second, scenarios. Now, the title of this talk was from 10 days to 10 minutes. And in an embarrassingly parallel problem, that's actually not very hard to do. You just keep adding more cores until it'll scale linearly. So just keep adding cores and you'll keep reducing runtime. So that's not really the interesting part. The interesting part is that with only 200 instances, we get 307,000 cores. That's because we basically have a higher core density. So by using GPU, you could go and start a whole bunch of traditional instances in AWS, like cluster compute instances, but you're going to need a lot more of them to achieve the same throughput. And that ultimately is a cost question. So
I just want to make one comment regarding cost question. And when we were talking initially, I asked Amir, like, how do you choose these servers? They just said very clearly, we just look at the cost. And we are calculating our costs. We are looking at the problem on hand. And that's how they are calculating, choosing their platform. It's very straightforward, and that's how they do decisions. And these numbers are actually over there, yeah?
Right, yeah. The metric we look at is our throughput per dollar. So we define throughput as how many scenarios can I simulate per second? And then how much does it cost me to run that for that 1 second or 1 hour, whatever. So scenarios per hour. So that's what we mean, and it's a straightforward calculation. So whoever gives us the best throughput per dollar that's where we'll go. And currently we believe it's with the GPUs. And the ones in Amazon and AWS are quite good and cost effective. So in our world, the insurance companies, an example would be, okay, the insurance company needs to run a monthly report, a risk analysis, and they have like 1 million policy holders. So each policyholder has to be simulated individually. Within each individual simulation could be, say, 20,000 Monte Carlo scenarios. And then we have to rerun those simulations for each policyholder, say, 10 times, because we want to look at different shocks. So you say, oh, what happens? The market goes up 1%, down 1%. There's all these perturbations that need to be done, which, again, multiply. So we have 1 million policies, 20,000 scenarios per policy, times 10 shocks per policy. It's a pretty big calculation. And then it gets bigger than that. Actuaries, they love to come up with complicated simulations. So if we took like a 200 core grid, traditional CPU grid, and it's using some legacy software, and there's a lot of suboptimal things going on there, but it takes like 10 days to do this. So half the month is spent just scrambling to get the report done for that month. And they have a limited budget. They can't just go buy like 20,000 cores and host them in their closet or wherever. So, but with AWS, you can do this in 10 minutes. The GPU processors give us about a 50x. So just looking at, okay, if we had one server in your closet versus one G2 instance, we're getting like 50x increase already. Now, your report is going to take 10 minutes, so we're just going to start 200 GPUs per an hour. That's all it costs, other than reservation or something. But that's a lot cheaper, and it's a lot faster. So it's kind of a no-brainer. As I said, like 307,200 cores. If you try to do that with like Intel CPUs, even if you use the AVX vector processors, you're still probably going to end up paying more. Just a quick note on, I'm going too fast. Just a quick note on our software. So one thing I said was that we're in a continual search for the optimal platform in terms of throughput per dollar. One of the issues with GPUs is that they're very difficult to program. You can't just take any code and run it on GPU. You have to rewrite it, possibly and drastically rewrite it. So if you have like really traditional sort of like object-oriented, huge class hierarchy kind of machinery in your program, it may not run very well at all on a GPU. GPUs work well in kind of it's like a Fortran world. You can run C++ on it, but you're not going to use like all these virtual classes and things like that. What you're going to do is just have what's called a kernel, which defines what happens in a single thread, and it's like a kind of a recipe book algorithm, and as straightforward as possible. We're trying to do like micro optimization and stuff. We're not interested in paying any abstraction penalties. So highly abstracted legacy financial risk systems are very difficult to move to GPUs. And for even if you were just starting from scratch for an ordinary quant or actuary, I shouldn't say ordinary, but for a quant or actuary, they're very bright people, and they could read the manual and learn how to program that device if they're ambitious enough. We're kind of working in a raw C, C++ environments, and they're not professional programmers, so they might create a memory leak or something, and so that's one danger, and it'll take a long time to implement. So high performance computing has some, sometimes people talk about high productivity computing. So okay, it took you like 10 minutes to run your calculation, but if it took you a year to implement it, then that's not very good. And then you can write very fast code. The faster you want it to go, the more hardware specific you start becoming. So you have all these optimizations that are specific to the particular architecture that you're targeting. And the history of high-performance computing has been fickle. Entire processor architectures appear and are axed. IBM cell processor, for example, or a whole bunch of things in the past. So you could spend like $1 million implementing some super high-performance stuff that only works on this one architecture, let's say GPUs or whatever, and then you find out that the hardware vendor is changing or axing this, and something is, you're out of luck. So these are the types of problems that arise that kind of prevent adoption. We deal with this we developed our own domain-specific language. So we have a compiler, a language, very simple one that actuaries, quants will understand. It's kind of like a spreadsheet type of thing. So really straightforward. It's domain-specific. That means that it's really constrained to the problems that we're trying to solve, financial Monte Carlo. We're not trying to build like a tool to solve everyone's problems. Just so by constraining the problem set, we are able, and specializing our solution, we can get away with just creating our own programming language, our own front-end compiler, and just compile to, you want to run a GPU, CPU, Xeon Phi, whatever you want, just change a compiler flag and it'll run. In addition, traditionally compiler designers, they think about it in terms of really running on one core. That's what the goal is, to take some logic and make it run on one core. They went further, and there are things like there's various extensions, ACC and things like that, where the compiler will, or OpenMP, the compiler will parallelize your program. So you write a for loop, and it will figure out how to run that on vector AVX process, vector instructions, and multiple cores and threads, and it'll launch the threads for you and manage the thread pool for you. The compiler is doing this for you. You just write a for loop, but still running on one processor. But our kind of view on this is that from a compiler design and domain-specific language design perspective, our target is AWS. So when we write a program, the compiler takes care of all the complexity of like AWS API, run the cloud, start the instances. We have our own, in addition to AWS API complications, we have our own like middleware, so we have TCP/IP socket code to actually distribute this work to all these nodes and then gather the results. And there's a lot of specific optimizations that go on there depending on the particular calculation. So all that can be abstracted away through domain-specific languages. That's what we do. So we give the quant or actuary an interface where they just focus on the business logic, business problem. The compiler takes care of everything else so that once it's done, click a button, and their simulation will be able to run on like 100 GPUs on an elastic cloud without them ever having known anything about GPUs or AWS APIs. I was just going to say one other thing about this is, so I spoke about the failure of Dennard scaling, which prevented companies like Intel to be able to keep cranking that clock rate up. We should have like 20 gigahertz CPUs right now if it kept going. We don't. And so they fall back to this multi-core thing and GPUs, and it's hard to program, and okay. But you can keep adding cores. So, they have 2,000 cores. It's not clear that even this will continue. There's optimists and there's pessimists, but as risk-oriented people, we consider both possibilities, but one possible outcome in the future, in the next few years, is the end of Moore's law. So that would be the end of a 30-year exponential, that's kind of a really big problem. And if that were to occur, then probably what would happen at the end game is specialization. So if you can't just keep adding cores, then you're going to start seeing specializing processors to do particular things. And the reason we don't do that now is because there's cost issues, but it's also hard to program. You need to specialize on a new architecture. It's a huge pain. And the whole tool chain needs to be set up for it. But in the absence of Moore's law, there's a competitive landscape. It will probably lead to specialization. And again, we believe that the best way to deal with that type of situation is domain-specific languages. So keep your business logic far away from AWS conference, but maybe there's another cloud somewhere out there, and you could target that too. So it's just a way of doing abstraction without sacrificing any performance. So that's why we use DSLs. I think.
All right. So usually I do the cool talk in the conferences, like AWS cool technology. And now it's like gearing down, now we don't have so sophisticated things. Because after talking about GPUs, how they work, when it comes to AWS, it's actually, to be honest, quite straightforward. And we don't have the cool part anymore now because Aon is doing the all cool work. Actually, Amir and I talk how can we make this cooler? And we went with the 3D icons so that, it looks fancier. So I apologize for my voice. This is the 5th day of the conference, and we've been talking and talking. It's good. A lot of people are asking a lot of questions. One of the key things, as Amir mentioned, is that this is flexible. At one end, there is a user of Pathwise application on a desktop running some simulations, At the client side, it's a nice, fancy software. What if those questions? On the other end, the huge data centers are provisioning themselves. That's a really nice thing. The nice thing is that this is a multi-ended architecture. On one end, Aon is managing the pieces. On the other end, the customer needs to connect to this infrastructure. And also this is a dynamic nature, both the infrastructure and Aon doesn't have one client. So they have so many clients. Imagine the pain every time you onboard a new customer, and these customers come with demands. You are going to a data center. You are actually installing servers, getting the software, licenses, building this thing, making sure you validate with customers' data center people, customers' network people. Actually, sometimes, Aon is very open. We work together. We are partners. Sometimes they deploy in the data centers as well. Those are the times when I lost Amir. I said, Amir, where are you? I'm in a data center. We are building this new thing. It takes long time. That's all I can say. The thing is, because we all know when you are provisioning in data centers, it's taking time. So let's talk about this picture very basically. Aon is leveraging VPCs. VPCs are completely isolated private data centers. Basically, you can say that virtual data center. So the customers are not actually operating in the cloud out of nowhere. We exactly know where they are. So And also, Aon is leveraging availability zones, which is like multiple data centers. So they are not deploying a single data center, they are actually going multiple data centers. So the connection they chose, I mean, they are okay because they don't have high throughput bandwidth in between the application, and they are very bandwidth hungry, but in between their clusters, but not from the client to the backend. They are using internet. The good part is when you are doing internet, you can actually, terminate firewall IPsec tunnels on AWS. And they had a policy. They said, look, we know AWS, you provide IPsec termination, which we do, so clients can build IPsec tunnels. But their policy said, oh, we are always using brand A, okay? Like we don't use your firewalls, we want to use our own. AWS is always bringing that, so they deployed their own firewalls, not our firewalls. So they are actually going to their own firewalls, and their firewalls do a gazillion secure things. Financial services clients, let's be very open, they want more and more security, and it's there. It's not like an optional thing. I mean, you want more security, you want DLP, you want IPS, you want whatever you want, you can install that because at the end, we are providing low-level infrastructure, you can build anything on it. And today, I mean, there are many security vendors, you probably met them, like you can just bring their own solutions. You just talk to your favorite vendor and say, how does your solution work on AWS? You can get that. So basically, this is all redundant too. So currently, they are leveraging multiple regions as well, so they have the ability to deploy different parts of the world. Every connection is redundant. AWS doesn't provide single point of failure. I mean, that's how we build services. It's always scalable and redundant. So this service runs. This service runs if there's one VPN tunnel fails, if one thing in those gateways, even like you see internet gateways, there is no gateway failure or gateway performance problem. Those things just simply scale. And then what happens at the end? Actually, if we go one more slide, it gets fancier in 3D. That's how we make it more interesting. So basically, this is the architecture. So they are using different isolation segments within a virtual data center, very much like your data center. So they are using subnets, and these subnets are isolated from each other with several different security controls, in addition to controls in the application. So yes, in one end, we have auto-scaling, GPU clusters. Lately, as Amir said, we are working on the G2s. Everybody wants, that's what I was telling to my friends actually. I want that 1532 cores, Now we have the 16 terabyte, and not that we are using here. Now we just announced the 16 terabyte EBS volumes. Everybody needs one of them at home, It's like, so those are really nice. But it doesn't work just with this GPU cluster. It's just one part. You need so many auxiliary services. You need to move files. You need to do certain things. So actually, Aon is deploying all those services. We call the shared services in a separate subnet, like the Active Directory. That's a key thing, right? You have to have your Active Directory, and it's there. And they have the file servers. They have the proxies, patching. You have the patching servers over there. So you can deploy all these things like on AWS, and you can build actually multiple service points. And I'm repeating this. Aon builds this for every client. It's not like they build a colo and inviting everyone guests to come and use this infrastructure. Usually, cloud is multi-tenant, but the way this is quite isolated. So every client gets its own. They are not actually sharing a lot. I mean, good or bad, financial services companies are not very sharing. So this is really nice. And
I would say, I talk a lot about GPUs, but as a SAS operator, for each client, we need to basically spin up an entire enterprise environment. AD, okay, you have 3 departments at the customer. They all need to log in. They have different access rules, and it's an entire enterprise IT environment, essentially.
And we make every team happy. Like we have the DMZ, we have the security, we have the IDS, and there are a lot of log servers. Everything is logging, logs are monitored. So the whole enterprise ecosystem, I call the mini data centers, are just spinning up. So it's actually working. And all these subnets are, I mean, if you were in one of the VPC sessions, you know, they are all inter-routed with a virtual router. Again, that router never goes down, never run out of capacity, or you never spend time configuring it. Technically, most of the provisioning can be done in an automated way because the whole AWS architecture is, at the end of the day, is a code. So you can send some code to the infrastructure, the things can build upstairs. I'm not saying you provision all the servers automated way, which you can, but the thing is provisioning the infrastructure, these virtual data centers, the subnets, the routing, the security groups, address translation, all these things can be automated. And AWS keeps adding these services day by day. For example, just a few weeks ago, now we spend a lot of time how to make Active Directory work on VPC, which it does. You can bring your own build. Lately, I mean, now AWS is offering like built-in, directory services. So you can do a lot of things easier and easier. And to be honest, this was the real thing. It looks like this in an uglier presentation. But so they have the DR. DR is built in. So because, again, everything has to be redundant. Everything has to be highly available. The same subnets, and so it says east in two of them, but one of them is not east. Then they can go intercontinent as well. Currently, we are using the VPN tunnels. So the flow is internet gateway to the firewalls, firewalls to either DMZ, to the other domains. And so everything is controlled through firewalls. In addition to firewalls, there is IDS, there are management servers, there are file servers and GPUs, so everything works together. So that's basically the content. We have like 7 minutes left.
I would add, like as a SaaS operator, the cloud, so we've done both. We run Colo SAS Operations and AWS SAS Operations. I would say the biggest pain points that AWS solves is at the beginning and the end. So in the beginning, you need to spin up this huge thing, like buying and racking and stacking servers, and that takes like 6 months and is incredibly costly, and it's just very frustrating. And it's to keep adding new clients, it becomes a real bottleneck. And then at the end, 5 years down the road, you have this jumble of wires and some cages, you don't remember it, you go see it, and like, how are we going to move this thing, upgrade it? Like, it's a major logistical operation at that point to figure out how to keep this thing going. And then in between, when we have hardware failures in our own colo facilities, again, it's like, if we're managing things down to the wire, like it becomes our problem to get the server vendor in and authorize them into the cage, and it's just something that, whereas in AWS, even if there is a failure, we just start it again and that's it. Yeah. So we can move a lot faster.
Yeah, that's also very important. Many people, I'm like that. I'm an engineer. I said, I can build this, bring these things, servers I buy and build those things. There's a huge operational aspect of this scenario. In the back end, to run something always on, always available. For example, and you need a lot of people to make this work. AWS, not that like we just want to make this for GPUs. In order to run this operation, you have to have a lot of operational standards, a lot of people, a lot of good resources to make these things operational. For example, all our GPUs are actually running on our EC2, which is like, can you imagine these are super performance servers running on a virtualized hardware? This is a lot of engineering problems in itself. Like we are running in order to make this work, we did a lot of engineering. It's not like, that's cool. On my VMs, let's spin, let's put my hypervisor code on this hardware and everything works. It didn't work that way. Actually, at one point, we had a lot of troubleshooting and everything. At one point, we even looked at basically the core calls that Aon was making. So our engineers, we brought up the engineers, and they said, okay, these type of calls work better than the other calls, so let's replace these calls with the other calls. So the thing is, it's a good feeling as well, because yes, Aon has the domain knowledge. They are good in what they do, and when it comes to infrastructure, we also bring up the other end, so that they both work together, as long as you have the operational consistency in place, because in the back end, we make this always on. All right. Questions? Yes.
What percentage of workloads are running on AWS right now? And do you have plans to migrate based on this? Seems like a successful.
We're moving all our SaaS customers to AWS. Some customers have a hybrid solution where they need to run some stuff in their own premises, but if we're going to run servers, they're going to be in AWS.
Mm-hmm.
So, is there any latency issues? Because it's all 10 gig.
Yeah.
Is there a plan for going towards high-speed interconnects like Ethernet?
Yeah. The G2s are right now not 10 gig, but we are looking at it. But there is definitely questions on that end. Networking, I don't know if you've seen one of the presentations. Networking is one of the most challenging things when you do data centers at scale. And what we did with networking and the consistency, because if you say, if you're an engineer, you will know, like, if you do TP50, P50, P90 statistics of latency, like how we are doing, it's perfect. But if you go P99, even P99999s, then it's really, really scary, because in this type of operation, you have to really, really consistent things. What AWS did in terms of fixing this network, like always getting the same performance, same latency, evenly distributed things. First of all, we develop a lot of networking infrastructure gear. So, we're all engineers. We can always build something, but AWS can afford to build this because of the size. That's a great privilege. That's what we did. The second thing, maybe you follow the announcements. We did a major shift in the networking recently, which is SRIOV. We had rewritten all drivers. Right now, the VMs are actually directly hooking into the hardware. It's called enhanced networking in the documentation. So when you enable enhanced networking, we are actually improving this packets per second performance and the consistency of the network a lot. And the GPU platform is actually getting that, not getting that at the moment, but we are looking at integrating that very soon.
From our perspective, like the types of Monte Carlo simulations we do are, because they're embarrassingly parallel, there's no major communication between GPU nodes. They don't talk to each other. If you were doing like an n-body physics simulation, yeah, if you look at like Cray big iron supercomputers, they have like these toroidal specialized networks where you can talk to the computer next door and it's faster than the one 6 nodes over, and that's definitely very specialized. That some problems would benefit from that.
Other person is Active you mentioned implemented in the Amazon cloud, and also you have Active on your premise.
Yeah. Definitely. You can extend, because we privately extend your data center. So consider this as an extension of your data center, completely private IP addressing. So you can extend your Active Directory, you can do one-way replication, you can do full bidirectional integration with an Active Directory like a Windows server. We are a big Microsoft partner with all Microsoft servers. You can do that. You can also use our directory service today, and you can also do one-way, two-way replications or completely standalone. They all work. pretty much?
Yeah, there's para-virtualized, what I was mentioning before, that they did a lot of work on the hypervisor. So we get pretty much direct hardware access to that GPU, and it appears as a CUDA device in our instance. But there is a hypervisor there. There's like a 20%, about 20%.
But on AWS systems, you see it as just another server. And so you can, it's another thing. I mean, maybe you have a great GPU idea. It's not like that 6-month process, you provision the hardware and do things. Tonight or right after, from your phones even, like spin a few of them and then you see how they're running. A few dollars, $5 maybe. Yes.
Do you have any interest or do you have plans to migrate to any or utilize any of the other Amazon services? Like it looked like from some of the slides that you're using a messaging service, you're using SCCP, you're using AD, SQL, lots of things that there are other.
I think our next focus will be on high-performance IOPS and SSDs, because right now we do everything in memory, but really we need to store things on disk, either as outputs or more frequently, if we're doing a long-running calculation, like 12 hours, we need to checkpoint and to save the state periodically, so if in case anything goes wrong. And that's where there's a big performance penalty. So we want to kind of move away from the purely in-memory view to, right now we view disks as like third world, like we don't want to go there ever, but if we can get high-performance disk writes, then that would be a big deal.
All right, we will take the questions, but we are just flashing red right now. But thank you for coming here. We'll be happy to follow up with the questions. Thank you.
Amir, nice to meet you.